तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the second lecture on the PN junction and 20th lecture of this course. In this lecture, we will continue with the analysis of the PN junction. In the last lecture, we have outlined the characteristics that we seek to explain. Then we saw how a PN junction is fabricated and what is the real device structure. Then we have also shown what are the approximations we make in arriving at the idealized structure based on which the analysis is to be carried out. We also gave a very simple qualitative explanation for the rectifying nature of the current voltage characteristics. Now we take up the analysis of the junction in detail. So as we explained in our introduction on the PN junction, we start with the analysis of the PN junction without any applied bias. That is the starting point. That is, we start with the analysis of the PN junction under equilibrium conditions. So this is the structure, a P plus N junction. P plus N means the doping on P side is more than doping on N side. The widths of this P and N regions are WP and WN. We assume that these widths are sufficiently long, that is much more than the diffusion length of minority carriers in the respective regions. Then we have made the abrupt junction approximation, which means that the doping changes abruptly from the P side to the N side. And then we have assumed that these two regions are uniformly doped. So the doping is constant in these two regions. So first step in the analysis will be to get the concentration of electrons and holes as a function of distance. We have said that the purpose of device analysis is to get N, P, Jn, Jp and E as a function of x within the device. Once you have this information, you can always get terminal characteristics which are of interest to you. So let us start with N and P, that is concentration of electrons and holes. The concentration of holes will be more on the P side than the N side. Okay? So let us call this as P, P. And since we are considering equilibrium conditions, this is PP0, and this will be similarly PN0. Analogously, this is the concentration of electrons on the N side, so this is NN0 and this is NP0. Notice that these concentrations correspond to the regions which are far away from the junction. This is because we expect some variation in the concentration around the junction. Because the doping is changing abruptly, the concentrations of holes and electrons have to change. So far away from the junction, however, the regions are same, the conditions in the regions are the same which would have been if these two regions were isolated, that is if the junction was not present. Now, we know that though the doping changes abruptly at the junction, the concentration of free electrons and holes cannot change abruptly. This is because if the concentration were to change abruptly for electrons and holes which are free carriers, then that would result in infinite diffusion current, and this is not physical. So the concentration has to change gradually. So from PP0 to PN0, you have a gradual change in concentration. something like this. And this line should be continuous, because any discontinuity would mean infinite diffusion current at the point of discontinuity. Now here I want to mention that we have shown the extent of this region over which the variation occurs on the N side to be more than on the P side. The reason for this will become clear as we proceed further. Now similarly, we need to sketch the electron concentration variation from Nn0 to Np0. Now when we do that, we should note that this concentration line should pass through this point. Okay? Now what is that point? This is called the intrinsic point. This is because under equilibrium conditions, the concentration of electrons and holes, the product of these two is Ni square. So when you plot it on a log scale, which is what we are doing, this is log. Okay, concentration on a log scale. We are plotting the concentrations on a log scale because we want to show both the majority and minority carrier concentrations. So when we are doing that, as pointed out in an earlier lecture, the Ni point will be exactly in the middle of these two, right? So this is Ni. So on a log scale, since Nn0 into Pn0 is Ni square, Ni is midway between Nn0 and Pn0. So therefore, this point, the concentration of holes is equal to Ni. So this is called the intrinsic point. So since the device is under equilibrium, the product of electron and hole concentration should be everywhere equal to Ni square, even if they are varying. So since Pn is equal to Ni square, this Nn0 to Pn0, Np0 variation, line describing this variation, should pass through this point. So let us draw that. Now, what we will explain shortly is that the intrinsic point lies on the lightly doped side. This is heavily doped side, this is lightly doped side. The intrinsic point lies on the lightly doped side. And this statement is related to the fact that the extent of variation is more on the N side than on the P side. Now, if we were to sketch the same variation of holes and electrons on a linear scale, let us see what would it look like. Let us take a typical example. Let us say the doping on this side is 10 power 16. Okay, so Na is 10 power 16. And Nd is 10 power 15 per centimeter cube. Then this line is about 10 power 16 because we will assume complete ionization and neglect thermal generation. Majority carrier concentration is almost equal to doping level. So this 10 power 16 per centimeter cube, and this is 10 power 15 per centimeter cube. So since Ni is of the order of 10 power 10 per centimeter cube, exact value of Ni is 1.5 into 10 power 10, but we are just interested in the order here. So that being the case, this Pn0 will be of the order of 10 power 5 per centimeter cube, and this Np0 will be of the order of 10 power 4 per centimeter cube. because 10 power 4 into 10 power 16 is 10 power 20, which is square of 10 power 10. So you see that 10 power 4 to 10 power 16, 10 power 12 variation, that is 12 orders of magnitude from this point to this point. So if you divide this interval into 12 equal parts, then the 1/12 of this would correspond to a variation in the whole concentration by a factor of 10. So which means if you divide this into 6 parts, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 equal, these are not equal right now, but you assume that they are equal, then 1/6 of this would correspond to a factor of 10. So that is somewhere here. So this, if this is 10 power 16, this point is 10 power 15, close to that. So as shown here, this is not exactly to scale. So if you plot this on a linear scale, it would look something like this. By this point, when it has come down to 1/10 of the value, it would be 1/10. This we are plotting on a linear scale. So to avoid confusion, I will now remove these numbers. So this is linear. Let us do the same exercise on the other side. 1/10 of variation would occur somewhere over this region. So if I were to show on a linear scale the same thing, then it would be something like this. So you have, this is 10 power 15 per centimeter cube, and 1/10 of this is somewhere here, 10 power 14. Okay? So on a linear scale, the variation is much more rapid than on a log scale. I will remove this number to avoid confusion, and this is n0, and similarly on this side this is p0. We cannot show Pn0 and Np0 at all on a linear scale. Further, we have used a different scale on these two sides. Please note that Pp0 is 10 power 16, Nn0 is 10 power 15 in our example. So 10 power 15 would be 1/10 of this. So strictly speaking, this side should be shown 1/10 of this. So this interval should be 1/10 of this, but then it will not be very clear. So again, we are not drawing this to scale. This is important to note here. So scale on this is different from scale on this. Now, what this particular plot on the linear scale shows is that these two regions seem to be almost totally depleted of any carriers. You see that the carrier concentration is dropping to almost 0 on a linear scale. That is why the region next to the junction on either side here is referred to as the depletion layer, because in this region the free carriers are totally missing. That is how we come to the concept of depletion layer. So the width of the depletion layer is, let us say, this width is xp. This is on the p side, so this is xp. and on this side this width is xn. So the depletion layer width is xd equal to xp plus xn. So this whole distance is xd. The depletion layer width. Now what is the consequence of the depletion of free carriers on either side? The consequence is that you will have space charge, because the space charge rho is given by q into p minus n plus nd, assuming complete ionization of dopants. This is on the n side. On the p side, the corresponding equation q into p minus n minus na. This is the equation for space charge in an n region and in a p region. Now in a depletion region, p and n are almost negligible, 0 in this region. There is a rapid fall in n, rapid fall in p. You cannot show n here because they are minority carriers, they are very small, and minority carriers here also are very small in number. So your space charge equation is p and n we can neglect. So on the n side, this means that you have a positive charge of q times nd, and on the p side similarly, because we are talking of depletion region, in the depletion region you will have a negative charge q times minus na. So if you show the space charge here, okay, so here we are going to show rho versus x. X is this direction, okay, this is x. Then it will look something like this. Where this is q times nd and this is minus q times na. So this is a space charge picture, rho versus x. Normally what we do is we make what is called a depletion approximation. That is, we assume that this entire region is totally depleted of free carriers, though actually it is this region that is depleted of free carriers, and there is a region over which the variation occurs gradually. So the space charge is changing to 0 gradually here towards the end, but we will ignore this small distance, and for simplicity we make the approximation that is called complete depletion approximation. So in this approximation your space charge will be shown like this and like this on this other side. Okay, so this is the so called depletion approximation, complete depletion. Okay, so the same applies to this line. This is done to simplify the analysis. Now please note, assumption of a space charge picture like this is equivalent to assuming that the electron concentration changes abruptly at this point to 0, okay, and hole concentration changes abruptly at this point, which is obviously not true, because you see that if you were to show this on a log scale, if I were to show the complete depletion approximation on a log scale, then it would mean that I must assume Nn changes from Nn0 to Np0, that is electron concentration N changes from Nn0 to Np0 abruptly here, something like this, and Pp0 also changes abruptly. Now obviously it would look like a gross approximation if shown on a log scale, So that is why it is important to note that both log and linear scales are necessary. So you must show the information on both the log scale and the linear scale to get a complete picture. The log scale distorts the real picture. The linear scale shows the correct picture about the variations. But then we have to use the log scale when our analysis has to show both majority and minority carrier concentrations. So log scale is useful, linear scale is also useful, and we must use both. But you must use these scales, the pictures drawn on these scales judiciously, okay, in the given situation. So to explain the validity of the depletion approximation, it is more useful to see the linear scale. And in fact, the log scale may give a wrong picture. It may try to give an idea that the depletion approximation is very crude. But when you see the linear scale, then you know that the depletion approximation is actually quite good. There is another point. Sometimes the students have difficulty that if you use a depletion approximation, you are assuming that the free carrier concentrations are changing abruptly at the edge of the space charge layer, that is here and here. How can that be justified? Because that would imply infinite diffusion currents. At this point, it is necessary to note that the approximation is used only for a particular situation. You should not try to derive the information from this approximation for other situations. So in this case, the depletion approximation is used to determine the space charge picture, and as we will see shortly, the electric field based on the space charge. So only for space charge and electric field calculations, the depletion approximation has to be used. Okay? So you cannot use the depletion approximation and trying to find diffusion currents and so on. Depletion approximation makes it easy for us to derive the electric field picture and some of the other parameters under equilibrium conditions. Now let us see what is the field picture for this particular space charge picture. Now the field picture is obtained using the Gauss's law. The Gauss's law says that dE by dx is equal to rho by epsilon, that is q Na by epsilon with a negative sign, approximately equal to, because this is a depletion approximation that we are using. So dE by dx is approximately equal to minus q Na by epsilon on the p side for this space charge, and on this side you have dE by dx approximately equal to q Nd by epsilon, that is for this picture. So which means that if I want to sketch E versus x, I know from here that since q Nd by epsilon is constant over this distance, dE by dx is constant, that means I should have a straight line for electric field as a function of x. So this straight line has a positive slope. So this is the way one can draw this straight line on this side. On this side, the slope is negative, minus q Na by epsilon. So it is something like this. Notice that I have to start from 0 electric field at this depletion edge, because the field does not exist beyond the depletion region. All the field lines from the positive charge on the n side of the depletion layer and terminate on the p side of the depletion layer where there is a negative space charge. So that is like this. So you have field lines starting from here and terminating here. So the total positive charge here, that is the area under this curve, is equal to the total negative charge, that is the area under this curve. That is why we are starting from 0 electric field at this edge and returning to 0 electric field at this edge here. This is a statement of charge neutrality. So overall the device is charge neutral. So this is dE by dx is qNd by epsilon, this is dE by dx minus qNa by epsilon. Now because of this charge neutrality, you have qNd, that is this height, into this width, that is xn, equal to qNa, that is this height, into this width, that is xp. So qNa xp is equal to qNd xn. So which means xp by xn is equal to nd by Na. So this clearly explains why xp is less than xn if nd is less than Na. In fact, xp and xn are in the same ratio as the doping levels. So if you take, for example, Na is 10 power 16 and Nd is 10 power 15, then xp would be 10 times smaller than xn. So that is why we have shown the extent of xp less than xn here. This diagram is again not to scale, because if we had to draw it to scale, we should have shown this 10 times this width. So in fact that is the reason why in this diagram also here this is much more than this. Okay, so most of the variation in the carrier concentration is occurring on the n side, that is the lightly doped side, where the width of the depletion region is more, and that is why in fact the intrinsic point lies on the lightly doped side. Okay, this point is on the lightly doped side because most of the variation is taking place here. Okay, now returning to this picture of the electric field, we can now sketch the potential variation based on this. The potential variation will be integral of the electric field. So I have a reference potential here which is, let us say, 0, and then the potential is more positive as you move towards the right. This is because the electric field is in this direction, which means this is more positive than this in terms of potential. So the potential will be shown more positive on this side. If you integrate the straight line portions, you will get a parabola like curve like this and like this. And then the potential is again constant. So this is psi potential versus x. Now this is the so-called built-in potential variation. Notice that most of the potential drop occurs on the lightly doped side or the n side. So this is a potential drop on the p side and this is a potential drop on the n side. So this is psi p and that is psi n. And this total potential drop across the depletion layer will refer to as psi naught. This is the built-in potential across the PN junction. Now, though there is a potential variation within the device from P to N region, please do not think that this potential variation is causing any current. Students have difficulty understanding this because they feel if there is a potential variation, should there not be any current? Now, there is a contradiction here. Device is under equilibrium, which means there cannot be any net current flow, because equilibrium means for every process there is an inverse process going on at the same rate. So obviously there cannot be a current flow. And also you can look at this structure here, there are no terminals connected to any battery. So therefore there cannot be a current flow. So the current at every point is 0, either for electrons or for holes. Okay? Then how can there be a potential variation within the device? Now, one way to understand this is as follows. This is the device, PN junction, and there is a built-in potential here. Direction of this potential is this. Okay, this is positive and this is negative. This is psi naught. If you were to join the P and N regions with a wire, no current will flow. Why? Because supposing we join, let us say some metal we use for connecting this region to the other region. So this is some metal. A current does not flow because between any two dissimilar regions there will be a built-in potential. Just like we have explained how there is a built-in potential between P and N regions, using similar arguments we can explain that there will be a built-in potential between metal and P region and between metal and N region. And the directions of these built-in potentials will be opposite to that of psi naught. So the built-in potentials across this contact and this contact will cancel the sum of these two will cancel the psi naught. So that using Kirchhoff's law, if you go around you get a zero change in potential and therefore no current can flow. Now how is it that there is zero net current? How can you explain this using this diagram? Okay. Now we can explain it as follows. We have seen how because of this space charge there is an electric field. We can call this as the built-in electric field. Whatever fields and potentials and charges exist under equilibrium, they are called built-in potentials, charges, or electric fields. So because of the built-in space charge there is a built-in electric field, and that field is directed in this way from N to P. So you have two types of currents, drift and diffusion currents. Now see what happens. If you take this point, at this point there is a gradient of electrons, therefore the electrons will tend to move in this direction because of diffusion. So I am not showing the current, but I am showing the direction of flow of charges. So electrons move in this direction because of diffusion, but then you have an electric field which is this direction. So this electric field will drive the holes, will drive the electrons in this direction. So you have the drift flow in this direction. Thus the diffusion tendency cancels the drift tendency. Because of exact cancellation of drift and diffusion tendencies in the depletion layer, you do not have any current flowing, which is how it should be, because this is equilibrium condition and Jn is equal to 0 everywhere and Jp is equal to 0 everywhere. So one can show similarly for holes. For holes, the holes tend to, at this point the holes tend to move in this direction because of diffusion, and this electric field drives them in the opposite direction. So these two tendencies cancel. In fact, based on this discussion, one can think of a thought experiment to explain the formation of the depletion layer. This thought experiment is as follows. You take a p-type silicon and n-type silicon and you join them. At the instant you join, the whole concentration is much more on this side than on the other side, because holes are minority carriers here and majority carriers here. Therefore, there is a diffusion tendency. This causes movement of holes from left to right. Similarly, because of the diffusion tendency of electrons, there is a movement of electrons from right to left, from N to P region. But this movement causes build-up of an electric field. If P region loses holes, it becomes negatively charged. Also, it is gaining electrons. That is another reason why it is becoming negatively charged. Similarly, the N region is gaining holes and losing electrons, so it becomes positively charged, and an electric field is set up in this direction. This electric field opposes the tendency of hole movement, and it also opposes the tendency of electron movement. So once sufficient electric field builds up so that these tendencies are opposed exactly or cancellation takes place, then this movement stops. So that is how the width of the depletion layer will be decided by this condition, when the transfer of charges has created an electric field that can exactly cancel the tendency for movement. Let us return to the analysis. Our analysis so far has given qualitative information about the 5 parameters, namely N, P, Jn, Jp and E. Okay? So N and P variation is sketched here in these two graphs. Then Jn and Jp are 0 because the device is under equilibrium. Everywhere Jn is 0 and Jp is 0. So we don't have to sketch a graph to show this. Then finally we have sketched the electric field, E versus X. So the qualitative analysis is complete. Now we need to make a quantitative analysis and get values of the various parameters, namely the width of the P and N regions, the width of the depletion layer on the P and N side, Xp and Xn, and therefore Xd. Then we would also like to know the value of the peak electric field, that is this, the maximum electric field which occurs at the junction. Notice that the maximum electric field occurs at the junction because this is where you have a change from the positive charge to negative charge. Okay? So we need to derive an expression for what is EM, maximum electric field, and then we also want to know what is the built-in potentials psi naught and the potential psi n and psi p on N and P side. So the parameters to be derived are Xd, Xn and Xp, psi naught, psi n and psi p, and EM, that is the peak electric field. Now as we have pointed out earlier, analysis of any device is based on the 5 basic equations. There is nothing beyond the 5 basic equations. Okay? At least in the first course, all this analysis for any device is based on the 5 basic equations, the differential equations. We have shown these equations in an earlier lecture. I am repeating this slide here again for the purpose of convenience. So the continuity equations, the transport equations and the Gauss's law, these are the 5 basic equations. So let us see how using these 5 equations we get the mathematical expressions for the quantities of interest. Let us start with the transport equations. Jn is 0 and Jp is 0 because of equilibrium. Now what information can we derive from here? So let us write the equation for, say, Jp. So Jp is drift and diffusion. So Q dp dp by dx with a negative sign is diffusion plus Q p mu p into E. This is equal to 0. So Jp is given by this formula, and this is equal to 0. We will show that we can use this expression and get the built-in potential psi naught, that is this value. Now, let us rearrange this equation. We use the fact that mu p into Vt is equal to dp. This is the Einstein relation. If you use this fact, then you can rewrite this expression as follows. The electric field is given by Vt by p dp upon dx. Okay, so the q is cancelling here, and you can cancel dp with mu p, and you can write dp as mu p times Vt. So here you will be left with Vt when you cancel. That is how Vt into dp by dx is coming here, and then you have p, so that comes in the denominator. So Jp is equal to 0 translates to this particular equation. Notice that dimensionally this is correct. This is concentration, this is concentration, so this cancels. This is voltage and this is length, so volts per meter, that is the electric field. Now we know that the potential psi naught is nothing but the integral of this electric field with respect to dx, okay, and the integration should be carried out from the p side to the n side. There should be a negative sign. The potential is integral of electric field with a negative sign, but since psi naught is the magnitude, okay, it is a positive value. Notice that psi naught is simply the magnitude of the built-in potential. Therefore, what we need to take is the magnitude of this result. So if you do that here, your integration would look something like this, is integral Vt into dp upon p. So this dx, and when you multiply E dx, this dx, they will cancel and you are left with Vt into dp by p, and you are integrating from p side to n side. And you have to take a magnitude. So integral dp by p is nothing but ln of p, and ln of p, so if you take p on the p side, it is pp0, and you take p on the n side, it is pn0. So therefore the result is, this is equal to Vt ln pp0 by pn0, that is psi naught. Is that pp0 is more than pn0, so therefore this is positive. So this is the formula for psi naught. This relation is also called the Boltzmann relation, which relates the concentration at any 2 points to the potential difference between the 2 points under equilibrium conditions. Okay, so in general you can write this equation as follows. So this is the Boltzmann relation. So it says psi 1, 2, the potential difference between 1 and 2 can be related to the concentration difference between the 2 points. Okay, psi 1, 2 is Vt ln P1 by P2 under equilibrium. Let us check whether we need a negative or a positive sign here. You see, if this is 0.1 and this is 0.2, and if P1 is more than P2, then there will be a tendency for holes to move from left to right. So this is the tendency for hole movement. It has to be balanced by the drift tendency. So this is diffusion tendency of holes. It has to be balanced by the drift tendency because this is under equilibrium. So that is, electric field is created. So the electric field should be in this direction, which means 0.2 should be positive as compared to 0.1. Okay. So if you write psi1 2 as psi1 minus psi2, then 0.1 is negative and 0.2 is positive. But since P1 is more than P2, this quantity is positive, so you should put a negative sign here. Now one can similarly write Boltzmann relation for electrons. For electrons, the relation would be same psi1 2 is equal to Vt ln n1 upon n2. Here there will not be a negative sign. Negative sign will be removed. Now this Boltzmann relation is obtained by considering the equation Jn equal to 0 instead of Jp equal to 0. You will proceed in the same way. You will write Jn in terms of drift and diffusion, then write the electric field in terms of Vt, n and dn by dx. So you will get the result as E equal to minus Vt by n dn by dx. You will get a negative sign here in this case. Then you can integrate this equation to get the Boltzmann relation. So that being the case, you have not just one equation for built-in potential. You could calculate the built-in potential either from the hole concentrations, or you could calculate also from the electron concentrations. So I can write the same thing also as Vt ln n0 by np0. So Jp equal to 0, Jn equal to 0 has given us the built-in potential of the PN junction. Next, we need to determine the depletion width. Once we know psi naught, how can we determine the depletion width and the peak electric field? For this purpose, we need to go to the electric field versus X diagram. So let us look at this diagram. Area under this electric field picture is the built-in potential psi naught. This width is Xn and this width is Xp, and this is Em magnitude. So we can write area under the electric field is given by half of Em into Xp plus Xn, and this is psi naught, for which we have already obtained an expression. Now we know that Xp upon Xn is equal to Nd upon Na. This we have shown earlier because of charge neutrality, because this area is equal to that area. Positive charge is equal to negative charge. Using this, we can replace one of these Xp or Xn in terms of the other. So let us write Xp is equal to Nd by Na into Xn in this formula. Then we get half of Em into Nd upon Na plus 1 into Xn is psi naught. Now we have reduced these two widths to one width. Now we need to reduce one more unknown here, because you have two, Em and Xn. Now how do we do that? Well, we know, again using Gauss's law, as you can see, if I take this slope here, then I can write Em upon xn, that is the slope of this line. So this is Em, this is xn. By Gauss's law, this is d by dx, that is qnd by epsilon. So using this, we can replace xn in terms of Em, so that this equation will be only a function of Em. Alternately, we could also replace Em in terms of xn, in which case you will get the value for xn. Let us determine Em. So we can write xn is equal to epsilon Em by q times nd. So this we will replace in this formula, and the result would be half of epsilon Em square by q times nd into nd by na plus 1 is equal to psi naught. Now if you put this nd inside, then you will get a much better looking expression. Half of epsilon Em square by q into 1 by na plus 1 by nd is equal to psi naught. So that Em equal to 2q psi naught divided by epsilon into 1 by na plus 1 by nd with a square root sign. So this is the formula for Em. Now let us get a formula for xd. Now this formula can be easily obtained using the equation psi naught is equal to half of Em into xd. That is, psi naught is nothing but area under the electric field picture. So this distance is xd and this is a triangle. So using this you obtain xd nothing but 2 psi naught by Em. But Em is already available here. So from these two you get xd is equal to 2 epsilon psi naught by q into 1 by na plus 1 by nd with a square root sign, where psi naught we have already determined is equal to Vt ln pp0 by pn 0, or you could write in terms of nn0 by np0. Now let us simplify this and get it in terms of doping, because everything we want in terms of doping level in the junction. So pp0 is nothing but approximately equal to Na, assuming complete ionization and neglecting thermal generation. Pn0 is Ni square by Nd, minority carrier concentration on the n side. So therefore if you put this, you will get the result as NaNd upon Ni square. That is the formula for psi naught. So if you want the parameters, namely xp and xn, once you know xd, you can very easily get these parameters, because you know xp by xn is equal to Na upon Nd, Nd upon Na. And using the same result you can also get psi p and psi n if you like. Let us summarize the results of our equilibrium analysis. Our analysis has shown that a p-n junction like this can be separated into neutral and space charged regions. The width of the space charged region is xd. Of this xd, xp is on the p side and xn is on the n side, where xn is related to xp by the formula xn is equal to Na upon Nd into xp. So this is the neutral region. These are the two neutral regions, and this is the space charge region. Further, our analysis has also shown that this space charge region can be assumed to be completely depleted of free carriers, and therefore a positively charged region here has a space charge given by the ionized donor atoms, and here the space charge is due to ionized acceptor atoms. Now, based on the depletion approximation, which is very important approximation for equilibrium analysis, we have shown that you can sketch the electric field distribution, the built-in electric field distribution, something like this. The area under this built-in field distribution is the potential psi naught, the built-in potential psi naught, which is given by Vt into ln of Na_Nd upon Ni square. This formula was obtained by using the transport equations Jn equal to 0 or the Jp equal to 0, transport equations under equilibrium. Then we obtained the width of the depletion region using the Gauss's law as square root of 2 epsilon psi naught by q into 1 by Na plus 1 by Nd. And using the psi naught and xd, one can obtain the peak electric field as minus 2 psi naught by xd. So this is how, starting with the basic equations of transport and continuity and Gauss's law, we have derived all the information. Note that continuity equation was not used because it is trivial in this case, because every term of the continuity equation on the left hand side and on the right hand side is 0. There is no rate of change of carrier concentration, there are no excess carriers, and there are no currents. Therefore, continuity equation was not necessary or not useful at all in this analysis.